All right, so we've got the trapezoidal rule, which isn't named after anybody. And then we have Simpson's method, which is based on the shape called, it's not a parabola, but it's a paraboloid, which means 3 edges are straight and the 4th edge is a piece of a parabola. All right, so as we improve our shape, we also improve our accuracy. So it's going to be an improvement on the accuracy of the estimation of our area. Accuracy. Please, though, be assured this is still an estimate. It's not exact. It's an estimate of the area. So just to officially get it in your notes, we're going to go from a rectangle, which grossly either under or overestimates. We're going to improve it to a trapezoid. And then we're going to improve upon that with a paraboloid. The idea is still the same though. You take an interval, you divide it up into a specified number of intervals, and then you find the area of each, instead of each rectangle, you find the area of each trapezoid or the area of each paraboloid, and then you add them all up. And it'll be more accurate than a rectangle. All right, so let's start with the trapezoidal method. The area of a trapezoid, well, we know what the area of a rectangle is, right? The area of a rectangle is base times height. Okay, B times H is the area of a rectangle, so I'm just going to write BH in that shape. A trapezoid also is base times, but there are 2 heights. There's a height on each side. There's a smaller height and a larger height. And so the area of a trapezoid is found by B times the height on the left, which we'll call height 1, plus the height on the right, which is height 2. And then because we're adding 2 heights together, we have to divide by 2 so that we don't have way too much area. So that's the area of a trapezoid. The value of the base times the sum of the 2 heights, the small one plus the larger one, and then divide that by 2. And so you'll do that successively by hand for, 4 or 5 different trapezoids. So let's try that. And then when you get to larger numbers of trapezoids, there's a trap program built in that I gave you yesterday as well. You may have seen that was already there. All right, so let's estimate the area. Okay, I have 10 minus x squared on 0 to 3 using trap sub 3. Okay, that subscript indicates how many divisions of intervals you're going to separate this into. So I'm going to make it easy on you. We're going to go from 0 to 3, and then we're going to just divide that up 3 times. So that all works out really nicely. So we want to have a picture of what this is looking like. We've got the function, which is a parabola, 10 minus x squared, so it starts at 10. I'm dividing that up 1, 2, 3. And I'm going to separate this into 3 subintervals. And I'm going to create trapezoids from each of them. Ooh, my scale is not good at all. That's all right. So each of the heights, as we descend on down our trapezoid, or down our parabola, at 1, when I plug 1 into the function, I get a height of 9. When I plug 2 into the height of the function, I get a value of 6. When I plug 3 into the height of the function, I get a value of 1. All right, so clearly my scale is not very good, if you can see where my 1 ended up. But That's all right for our purposes today. So we are going to create now trapezoids in each section. So I'm going to connect the 10 to the 9 and then create a trapezoid. So there is some missing space here. So is my trapezoid too small or too big? This is too small. All of the trapezoids will be too small. And so this is going to underestimate, but it's better than if we had done rectangles. And so I'll find the value of my first trapezoid. So this one would be the base, which is 1, the heights, which are 10 plus 9, and then divide that by 2. And so the area of the first trapezoid is going to have a value of 19 over 2. All right, the second trapezoid will connect I'm having trouble with that word, I don't know why. Connect the 9 to the 6. And so I'll have my second trapezoid. Again, it's going to underestimate that value. So the value of that one would be a base of 1 times 9 plus 6 over the value of 2, so that's 15 over 2. And then my third trapezoid will connect the 6 all the way down to the 1. And that trapezoid then would be a base of 1, 6 plus 1, and that's divided by 2, so 7 over 2. And so then we would need to summarize the addition of those trapezoids. So clearly it's an underestimate because we have a gap between the top of our trapezoid and where the curve is, but the trap value would be that 19 over 2 plus 15 over 2, so far that's 34 over 2, plus 7 over 2, so 34 plus the 7, so I've got 41 over 2 is the estimate of my trapezoid, which is an underestimate. For the trapezoidal method, when you say why it's an underestimate, hey. The underestimate has to do with the concavity of the shape. Because this is concave down, the trapezoids will underestimate the shape. If it had been concave up, the trapezoids would overestimate the shape. For a rectangle, it's not based on the concavity, it's just based on whether it's increasing or decreasing function. So your argument about whether it's increasing or decreasing, or whether it's an over or underestimate, has to be valid for the shape that you're doing. So what you would say for this is that trap 3 is an underestimate because f of x is concave down on this interval. Okay, trap estimation is always connected to concavity. RAM estimation is always connected to whether the function is just either increasing or decreasing, but this one is always based on its concavity. Okay, any questions on that? Okay, so now let's do it with paraboloids, and we'll see what the estimation comes up for that. All right, the parabolic method. So this was developed by, I don't even know what his first name is, a guy named Simpson, not Homer, but I don't know. All right, and so the area of using paraboloids. All right, it's base times, all right, and this one's kind of long, so you might want to make sure you have a little bit of space. it's h1 plus 4 of the second ones plus 2 of the thirds, and you do it all at the same time, plus 4 of the fourths, plus 2 of the fifths, etc. It just keeps going 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, until you get to the end. And then the last one is just plain again. So like H, Z, or however far we get. H will stop at, I don't know, the 20th or whatever. Okay, you get all the way down. Let's do N. Let's do N. There we go. So it's just 4, 2, 4, 2, 4, 2, except the first and the last ones are single. Now I'm not going to prove this whole formula to you. I'm just going to tell you what it is. All right, but then that would be way too much area. Just like with trapezoids, we added 2 things. We had to divide by 2. With paraboloids, you got to add all of that and divide by 3. The other thing that Simpson required for his method to work is that must have even number of intervals. It doesn't work for odd. Okay, it has to be an even number of intervals. So we're going to do the same problem, but we're going to make sure that we have an even number of intervals. So our example is still going to be the f of x being 10 minus x squared, and it's still going to be on 0 to 3, but we need to have an even number of intervals for paraboloids to work. So I'll see if I can draw this a little better this time. All right, so normally we were splitting it up into 1, 2, 3. How would we divide this up? How many subintervals would we need to have to make this be a nice number of subintervals but still have it be even? 6 of them, okay, to have 6 subintervals instead of just having 3. So instead of just doing 1, 2, and 3 as my subintervals, we're also going to have 0.5, 1.5, and 3.5. So we know that from our previous question that these were already 10, 9, 6, and 1. And so what we need to add into this are the other heights at 0.5 and at 1.5 and at 2.5. So this is going to be 1.5 and 2.5. And once we have all the heights, the formula just goes really quickly. So these will be all the way up here. So again, I would just encourage you to do this on your calculator with the table. And so I'm going to switch my function in my calculator to be 10 minus x squared, and I already have my table set at 0.5s, and so I can tell you what these are. So this is 9.75, and this one is 7.75, and this one is 3.75. And then we can do the whole calculation all at the same time. So we are going to do simp, and we're going to do a sub 6. So Simpson starts with how wide the base of every interval is. So now that we've done 6 of these intervals, how wide is every base? 0.5. So 0.5 times. Okay, and now what we need to do is start with the first height, which we came across, which was what number? What is the very first height? That's not the first one. The first one is 10. Okay, plus 4 times the next one. So 4 times 9.75 plus 2 times the next one, which was 9, and then 4 times the next one, which is 7.75, and then 2 times the next one, which was 6, and then 4 times the next one, which was 3.75, and then the last one is just by itself at 1. And then that whole thing divided by 3. So instead of computing everyone individually, you just do it all at once. So go ahead. I'm going to pause the recording a minute. Take a minute to type that into your calculator, and we'll kind of see if we get some agreement in. All right, so we get 21 as the result of our Simpson's method. If we compare that to what we had before in the previous one, we had 41.2, which is 20.5. So we are slightly more accurate. Okay, this one was off by 0.5 of a decimal. We are now at 21. When you get to higher numbers of Simpsons, then you just use your program just like before. But it will not work if you do an odd number of intervals. It has to be even. All right, we're getting close to being exactly perfect. We've gone from RAM, which had a high degree of error, especially if you use left or right. Mid was better. Went to trap. Trap is even better still. Simpson's parabolic method is even better. And then we get to what the exact one is. So the last thing I need to introduce you to today is exact area. Exact area is indicated by the following symbol. It's an elongated S. It comes from the Greek sigma, which stands for summation, and summation means the addition of many things. And because we are adding either lots of rectangles, lots of trapezoids, or lots of paraboloids, we summarize that into this symbol, okay, of an elongated S. The function would be written after it. The axis that the function is going to sit on is indicated after that with a dx. So you have the function, and then the d kind of means like on top of or with respect to, and then x would be that it's sitting on the x-axis. And then the way you know to start and stop is there's a number written at the bottom and then another number written at the top. So how I would write it for the problem I'm working on right now, I would write the exact answer like this. I would go 0 here is where I'm starting, 3 is where I'm ending. The function is 10 minus x squared. I put that in parentheses. D means sort of on top of or literally with respect to, and then the x-axis. And that would be how I would write that, indicating that I'm finding the exact area. So everything we have so far is an estimate, and then this is how you're going to do exact. Yeah?
Would you ever write anything different than dx?
Not in the, yes. When we have time being our axis here, then we would write dt. Okay, I think that's all we would have in this class. But eventually you'll do dy, so you'll be doing things on the y-axis, but in this class, dx and dt I think are going to be the only ones that we do. All right, so grab out your calculator, and let me show you where this is in your calculator. And this stands for the exact area. So you know our friend Math 8, right? Okay, so we have now our new friend is going to be Math 9. So go to Math 9, and my Math 9 pops up like this. If you have an older version of the calculator, it's going to look a little bit different, but my Math 9 pops up like this. If you have an older one, I'll show you what to do. And then you just fill in. This is the symbol for the exact area. So I fill in 0 and 3, and I put 10 minus x squared, and then I fill in x, and I hit enter. And the calculator tells me that 21 was indeed the exact area, and so Simpson's method was exactly right. Okay, if you have an older calculator, it just doesn't give you the little symbol. It might say something like FN int. Yeah. Okay, so let me show you what to do for that. So if you have that, oops. Oh, come on, you were just on. Don't be temperamental. Here, let me borrow your square. Just write it down on your paper, okay? All right. So if you have FN int, you've got to type in those. How many blanks did I remember when I had it, Math 9? How many blanks are there? 4. Okay, there are 4 things you have to put here as well. So, Math 9. You put the function first, 10 minus x squared, comma. You put the axis next, so x and then comma. And then you put the numbers 0 and 3 last with commas, and then hit enter. And that's also 21. Okay. It's a nice way to be able to check your work.